ROADEX e-learning seminar. Christopher Palo was normally opening this seminar webinars, but this time he just left a message that he's stuck in some other meeting and he will join a little bit later to us. So this time we will talk about 45-50 minutes about drainage and about drainage history in general. And drainage has been one of the key research issues on throughout the whole history of ROADEX project. So it was in 1998, even when we made the first application. So we were talking about drainage, and in ROADEX 1 already that was one of the main topic on research. And in this slide, what you can see is one of the first report and summary. What we did with Geir Berntsen and I, and we were comparing drainage in life cycle cost of drainage systems and roads with a poor and good drainage in Finland and Norway. And according to their calculation was that basically you could dig the ditches and clear the ditches every second year throughout the whole road network, and you would still be profitable on the road owners. So to say, the price to quality ratio in drainage management is extremely good. But it's probably also at the same time it's one of the most like the ignored measure in the road asset management and road condition management and it's a lot of discussion that why it is so much. I guess one burden is that what we've been joking that people think that it's so not so sexy to dig dirt from the ditches, but in general it's profitable, and that everybody should keep in mind because we are using taxpayers' money. So focus on the drainage can be seen also in when you are looking about a ROADEX publication. So from the ROADEX history, so we have already published already 16 reports on drainage. So it's a good number on drainage, and then there are also other studies and other publications in over there. And about ROADEX e-learning, we've been following also about people who are visiting and reviewing e-learning. So that shows also that it's not only on the northern periphery area where drainage is hot topic, but what in our review we have been finding out that all the time this drainage e-learning has been the most popular. And here you can see from last year, from May to October, about 4 or 5 months. So we have had about 6,500 visitors and on each month on the whole ROADEX web pages, but in this from May to October we have had more than 20,000 visitors only on drainage e-learning, and they are not just making a short visit because average time for staying in this e-learning has been 7 minutes. So they've been really looking for that. Also, the next slide shows on the drainage also that it's and in general ROADEX e-learning it is not anymore like northern periphery, and it's not so much related to uh, uh, like cold climate areas. But here you can see that, for instance, two most popular, the biggest number of visitors in ROADEX e-learning is India and Philippines, and they hardly have any frost. Maybe in India, in Himalaya mountains, but otherwise, and even for this Malaysia. So this has been very popular all over the world. We have hardly only 2 or 3 countries that have had not regular visitors on the drainage. But let's go for the start to go with the drainage e-learning package, and what can we find over there. First of all, the first lesson on drainage is what we call introduction, and where we are telling that why drainage is important. First of all, a little bit about history. Even Phoenician times were using drainage structures. Then about drainage design and maintenance, erosion issues, splash and pray. And on the right-hand side, you can see one really nice example about the benefit of drainage. This is from Ireland, about road N59, which was one of the test road when we did a demo in Ireland, and it shows the rut depths in 3 classes, and rut and also factors. So class 3 with the poor drainage, you can see that the rut depths are 2.7 times like bigger or deeper compared with the road sections where the drainage is more or less okay. So and that in Ireland is definitely, and you would see that its issue is permanent deformation when the water is present. And deformation in general is the main issue, what is causing problem, but also some maintenance issue like like soil verges or grass verges are causing problems, erosion issue, winter maintenance that we will talk later on this session, and of course it is traffic safety, aquaplaning, and so to say water rutting is one uh, parameter that we have to always keep in mind when talking about drainage. In addition, when you are in cold climate areas, drainage is a system is very much can be related to the differential frost heave and in frost action, and why is that basically in order to make ice lenses, there are basically three things what you have to have in the road structure, and one is minus degrees, and the other and is that you have to have unfrozen water and water available, and you have to have unfrozen water in the structures, and that's if you don't have water available, you cannot develop ice lenses. And here's one nice example of Highway 4 from Rovaniemi, where this private or bicycle path access road culvert is not working, so all the water is blocked here and flowing under the road and making a frost heave in which is more than 100 millimeter. Another issue when talking about low volume roads is on the right hand side. where we have found out also on the surveys is that for instance potholes can be related very much on potholes on gravel roads can be related very well on the presence of poorly working drainage, and especially in the springtime, which is right now going on here in northern Finland. If your ditches are filled with the water and the top part of the pavement structure is saturated, these potholes are developing, and one in the continuous monitoring of these roads, we have found out that when it gets saturated, even though you are grading, they are coming and appearing again within the few weeks. So these issues where you have to send a grader to make gravel roads even are very much can be related to the sections where your drainage has some kind of issue. Money, of course, is the one issue, and this is an interesting calculation you can find also on ROADEX website where we used the Swedish PMS object software to calculate life cycle cost for the roads, and relatively a lot with the relatively even road traffic volume, as you can see, as an average 500 AADD. But what this tells you that the thinner your payment structure is, the more sensitive your roads are for poor working drainage. So here is calculated assuming that in Finland we have about 60,000 kilometers of paved road, and if this payment and it's a typical average paved road structure in Finland. So if the drainage is not working at all, our annual cost would be roughly 300 million euro. If it's working, it's about 200 million euro, and with these structures. But if you go to 100 as an average, about 120 millimeter of pavement structures, the same corresponding figures are about 170 million on poor drainage, and if you have a good drainage, it's 100. So difference is less than 40 million when you are here talking about 100 million. So once wherever you have a thin pavement, you have to compensate that by focusing much more of your efforts on making sure that your drainage system is working and your pavement structure stay dry. Then from the motivation side about science and theory about drainage, and that we have a pretty good package over there about even starting to molecular level what is water and why it is important. So we've been developing, and what we are telling quite much like in this e-learning is that first of all that water molecules are in a way, when they are bound and when water molecules are absorbing from the air to the mineral grain structures in the pavement structure. So they are forming different type of layers, and the important layers in order to understand the performance is what we are called adsorption water layer, which means that very close to the surface the molecules are very well oriented with and the orientation is so tight that it equals very close to ice. Then the bonding is getting loose and loose until you are starting to talk about viscous water and capillary water. But thanks to this orientation, we can tell also that water, when you are talking about uh, what we call unbound pavement structure in general, for instance, in USA, many researchers are talking about waterbound pavement structure because water can also behave as a binder when you have enough compaction and water is very well arranged. It is actually uh, causing quite strong tensile forces between the soil or mineral particles in your in the pavement structures. Also, then about different forms of water molecules, as is it solid or liquid or frozen liquid, or if it's on the vapor form. So that is discussed. Then also we are trying to tell a little bit about the viscosity of the water and which is uh, causing this tensile strength. And here's one demo what we can exactly right now what we can see in and measure in the Berger stations during the spring thaw weakening. And here's a demo about electrical conductivity during the thawing period in the mineral structure. So this light blue equals frozen material in the pore water, and these dots are colloidal particles, which are always pushing uh, when ice is frozen, so colloidal particles are pushed against between the mineral particles and ice. And once the ice starts to thaw, these colloidal uh, particles are first coagulated, they are spreading, and later on they are flocculating. And when they are flocculating, then they are like making bigger grains and the electrical conductivity is increasing. But especially on this area where it is in this peak area, uh, when they are like spreading all the through like uh, equally like spread it all over the water, so the conductivity is high and the tensile strength is very low, and that is caused by colloids and colloid chemistry, like washing powders. I When we are using washing powders and cleaning our clothes, the it is exactly the same chemical principles on over there. Then water zones, where you have a groundwater table, capillary water table, and then what we call intermediate water zone, which is what we call in general the dry material, and uh, and also in that way what we compare back and try to explain very much on capillary forces and suction. In general, for instance, in Finland, suction has not been so familiar and has not too much been taught in the civil engineering, and we've been in general talking about only capillary forces. But right now in thermodynamics, this suction has been much more like it's much explains much more clear what are the how the road is behaving. Also, one important thing in order to understand the recovery times in the road is understanding the phenomenon that when is that air actually in the pavement structure, air is dissolving to the water, and that is part of the pore water pressures and how the occluded air bubbles are behaving. So this is especially in the and this can be related to the permanent deformation on the road structure. Then more easy and basic issue is which is still sometimes misunderstood and ignored, that what is gravimetric water content, what is volumetric water content, what is saturation degree, what is void ratio, and what is compaction level. So all this, in understanding that water content can be volume ratios, but it can be also mass ratios. And there are some tables where you can get a very nice idea that what is in which densities, what densities are when your material volume is, for instance, 70%, what type of densities you are having at different moisture contents on gravimetric and volumetric water content. This helps understanding the compaction issues. Also, water content is very much affecting an theory about water content in general, about that what happens when you are compacting water. If you are compacting water in dry, uh, below in low moisture contents, so you have to do a lot of force in order to break this bound water structure to get mineral grains, like good friction between mineral grains. But once you are, then the other issue is that if you are going higher than Proctor water content, which is optimum water content, then you are very you might be face of becoming like having problems with the positive water content and plastic deformation. So basically, for instance, this is a kaolinite clay with the 3 different compaction degrees, and normally the optimum Proctor content is on the phase where your capillary water is capillary, like in kaolinite, it's around 20 to 25%. So that is where your capillary water is still like a concave, this meniscus around between the capillary water and the air. So it is still like you get still quite good strength. Also about thermodynamics and seasonal change, understanding that when we are designing a road and making materials, we are assuming that pavement lifetime is a function of axles. But the fact is that if you are comparing a traffic amount and pavement distresses, and this is also results from USA, what you can find out that even though the traffic volumes over the year are almost the same, but 80% of the pavement distresses appear in winter and especially spring. And that means that it's not only pavement lifetime is not only function of loading, but there are also seasonal change has a major impact on our lifetime. And when we are talking of going to seasonal change in general, we on the thermodynamics, we have to understand in the future the suction. And suction is three type of suction. What we have to know is, first of all, in unfrozen material, it is a metric suction plus osmotic suction, which equals total suction. And metric suction is very much a function of fines content. So the higher you have, the higher content you have fines. So the stiffer is the material when it's dry, but it loses strength when the water content is increasing. It's like clay. It's a good example. On the other hand, osmotic suction is not depending on water content, and good example of osmotic suction is dust binders. If you put chlorides in your gravel roads for dust binding, so it causes so much tensile strength on between the particle that you don't have dusting problem. On the other hand, the third one important is understanding cryosuction, and cryosuction takes place when the material is freezing, and cryosuction forces can be even almost 1,000 times bigger than, for instance, normal capillary forces with a certain material. So this negative pore water pressure that is absorbing water to the freezing front can be extremely strong, and and understanding this tells very much why we have a certain failures in the pavement in the during the winter time. Then continuing water and mechanical properties, it's a lot of material, but one issue also, and this is a new understanding very much right now, is saturation degree and dielectric value. And very interesting finding, which we didn't know when the ROADEX started, but thanks to Andrew Dawson, who has been writing an excellent book, Water and Roads. So he had a theoretical idea, and he published that once the saturation degree is around 80% in normal aggregates, then air bubbles are occluded. And that means that if you are compacting the material or loading the material, these air bubbles cannot anymore escape anywhere. And that is increasing pore water pressure, or if you have a very high load, it causes that water is diluting to the pore water, and then in that case the water loses all these tensile properties. And what was really interesting that when we started to calculate then later on that this Andrew Dawson's theory about 80% saturation degree equals on dielectric value of 16, that on the ground penetrating radar data we knew that that is exactly the plastic limit where the, for instance, base course material loses its strength. So that starts to explain more what happens when we have wet materials and we are loading them. The other issue, which is also described, is hysteresis. And hysteresis in the pavement structure is one phenomenon that all pavement, all the road construction people know, that material at the same moisture content can be much stiffer when it's drying compared when it's wetting. And for instance, this is from my own PhD and Texas aggregate. CPR value, if you are multiply that 10 by 10, you get roughly moduli value. So at the same moisture content, when it's wetting, the material is wetting, it is 100 megapascal, but if it's drying, it's 200 megapascal. So that tells you the great difference, and that can be explained by hysteresis, which can be described as if you put a water droplet on the glass and then start to put this glass plate down, and so you are developing tensile forces on here, and that's the classical explanation of hysteresis and how it forms tensile forces when material is drying. Finally, also new thing that is now like explained in the updated ROADEX drainage e-learning package is frost heave, and especially these tertiary ice lenses. This is a new issue published and introduced by Swedish researchers from Technical University of Luleå, and that the term is tertiary ice lenses, and these are the ice lenses that are growing in frozen zone. And what I'll show that theory explains very much what we have been finding on roads, especially if you are not if you have delayed of snow removal. Also, this high suction is or there are explanation why this high suction forces and suction forces can be so, suction forces can be so high that they are developing, can develop ice lenses even inside the asphalt. And this example is from first winter from Kemi-Tornio motorway in Finland, where we had the problems on the top part of the asphalt, forming ice lenses because of de-icing salt. Then chapter 4 is explaining about components of road drainage systems. A lot of lists about and it is in general divided by 3 areas, what we called road drainage structures, dewatering structures, and then structures outside road body. And this road drainage and dewatering is interesting terminology, because for instance in Finnish language we have only drainage. It's only one word. It's kuivatus, which covers both drainage and dewatering. But basically dewatering in Swedish and English means that they are the structures that ensure that when it's raining, the road is removing really fast away from the surface of the pavement structure, and the drainage structure in general are designed to keep the whole the whole pavement structure dry. Then we are about the foresters ditches. We are publishing also, there are new information about the importance of keeping ditches enough deep. And here are some case studies about research studies of Pehko project, where we've been implementing this ROADEX know-how in Finland and tested. And this tells you about ditch depth as a function from the pavement surface and an annual RAT increase. And what you can see from here that anomalous in general main roads in Finnish Lapland, the anomalous RAT increase are mainly where the ditches are shallow, and the deeper the ditches are, the less you have anomalous structures. The same issue, even more clear and even better correlation even with the median values can be if you are starting to monitor ditch depth versus IRI. And then you see that once you go to a deeper ditches, for instance, ditches less than 70 centimeter, median IRI is 2. When you go 1.3 to 1.5, you are already 1.6, and if it's more than 1.5 meter deep ditches, average median IRI is 1.3. So to the road roughness and how smooth is the road, it's a clear correlation. Very important thing on also on the main road ditches is slope stability, and uh, and how important in the daily maintenance is first of all to check that all the ditches are clear, and immediately if you have some flow and ditches are get filled, you have to clean them. And there is, for instance, example about in this case that if this was not cleared, so in one year you would get immediately about 5 millimeter rotting, because all the water is infiltrated to the pavement structures. Also in many areas you don't have enough space to make open ditches, and or if you are in the mountain area, it's other issues. There are chapters and explanation about different type of subdrain structures and trench drain structures, and how they are built, and what type of things should be kept in mind on these structures. Then one issue, I don't have example, but there's a lot of explanation about outlet ditches, and what type of problems are there, and what you have to keep in mind when you are working with outlet ditches. But one issue, and these examples are from Scotland, is and what we've been hearing also from other part of the world is that if you cannot make outlet ditches for some reason, then a very good option is these infiltration wells and their structures, because you can, for instance, in national park, national protection areas where you cannot excavate ditches, but you probably can make infiltration well to ensure this water to infiltrate to the subgrade soil, and it can be very also environmental friendly structures. Then also experience and information about main road culverts, how you should install main road culverts, what are so to say no structures, and what are the issues you have to keep in mind when you are making and checking that your main road culverts are built in a good manner. Then about dewatering, one issue is pavement crossflow, and how do you build that, and how you make sure that pavement crossflow is made in that way that water is quickly removing from the pavement structures, and you don't have a risk for aquaplaning. But on the other hand, we are also in this case are showing example that that how important, for instance, is that you have a very smooth changes in the pavement crossflow, especially when coming to the curves or leaving to the curves, because as in the ROADEX reports about traffic safety and human body vibration, so it has been showing that it can be quite surprisingly about 50% of the truck accident can be related to a road where you have a rapidly changing crossfall. So this is also a traffic safety issue. Chapter 5 in drainage eLearning is drainage problems and how to avoid them. There are listed, we've been trying to find all the typical problems, what can be done, and what are the correct ways to do maintenance or road design, and what type of how you can fix these problems. And very simple explanation, and one, for instance, I just took one example that we can still see these mistakes, that once you are clearing the ditches, you are excavating the dirt or mud from the ditch bottom and putting them in the inside slope. and there is a lot of experience right now that if you are storing this mud over there or dirt from there, it is flowing almost immediately back to the bottom of the ditches. What you can even here see that already it's starting to develop crack on these areas, and it is only 1 or 2 years, and the material is back on the ditch bottom. The other issue, very new finding, what I already mentioned, is this snow removal from the road shoulders. It is that if you have a thick snow walls and in the winter time you have a warm days, and if this water from the snow, thawing snow start to flow, you are having at the same time you have a very high cruise suction in the base course under the pavement, and all this and negative pore water pressure. So all the water is flowing there. And when it comes again a cold days, it's freezing and forming ice lenses. And you can have like a 120 or 30% saturation level. And when this finally starts to thaw, you have a problem. You have a major deformations on this way. We have a very dramatic experiences about this phenomenon from previous winter in Pehko area in central Finland. Here's a nice example also that how clear you have to do work on that, which is this reflection balls. In the early days earlier, there were no machines that you had to go around when you were removing snow, and when we started to measure with the LiDAR laser scanner, we could find in road section that always on the snowball you get the high rutting. Even this amount of snow could cause a localized deformation on the pavement in these tracks, in these sections. Also private access roads. This is also Pehko research has shown that about 10% of the annual paving cost is can be increased by poorly working or poorly performed private access road drainage problems. And the issue is that it's not only on the access road, but if it's making pool above, so it can be where the pool ends, you get the first frost heap issue over there. Then you have a wet mud flowing to the ditches, and finally on this area you have the frost heap. So it can be a long area where this missing culvert or clogged culvert can cause problems. But also main road culvert, we are describing how to check them, how to process them, what are the methods, how to like check the condition, and how you can show where they are, and how you are checking the for instance percentage of how much culvert is filled. Then there are some technical description about, for instance, outer slope support and drainage structures. If you are in a sloping ground, side sloping ground, and your material is unstable and flowing to the ditches, then this kind of structures where you are basically making subdrain on the bottom of the ditches and then partly filling the ditches. Yeah, we've been testing this in central Finland, and these structures were made with the Tampere Technical University with very good experiences. Also, some more exotic solutions like hydroseeding, where you are stabilizing the surface with the sort of bio-glue and grass that is types that are making deep roots, and quite good experiences of these structures as well. And finally, sealing and patching, and remembering that that drainage is also when you are sealing the pavement. When you start to get micro cracking, and you can avoid of water infiltrating to the pavement structure by doing a sealing structures, surface dressing, etc. And there are some descriptions on that. Then drainage analysis and classification. Chapter 6, visual evaluation, laser scanners, ground penetrating radar, thermal cameras, and some new things is about aerial photos and images. So there are like a classical issue, how you are visually, and laser scanners can be visually and laser scanner based analysis. Also in special case, especially on gravel roads, thermal cameras are very good on finding ice lenses and evaluating that if you're where are the critical places on 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 the roads where which needs a special drainage attention. Laser scanner has been over the ROADEX time. Laser scanner is probably the best innovation that has been spreading for drainage analysis. And here's an example, for instance, from Scotland, Road 8 and 83, and where you see a water flowing, and then there's a private access road with a missing culvert causing bonding over there, and this water is now infiltrating to the pavement structures, causing this deformation. This is what you can see everywhere in the world where you are using LiDAR structures. Then we are also telling about how you are combining about laser scanner and GPR-based drainage diagnostic. How a good road with a well-working drainage system looks like a ground crossfall, where you don't have IRI rutting, you don't have a moisture, and then on the other hand, where you have what is the road where you have a drainage issue, and how the deformation looks, for instance, on the LiDAR, what we call LiDAR rainbow map is another way of getting a very visually very clear and understanding that, okay, now I have a problem. Then also laser scanner data is very good on quickly checking the ditch bottoms, because you can put a make a cross section and map where's the road surface, road shoulders, and where the ditch bottom. And once you have been doing that, and once you have been, for instance, have a ground penetrating radar for the pavement bottom, you can check if your ditches are as deep as they should be. And in Nordic countries, the specification that ditches should be at least 25-30 centimeter deeper than the pavement structure bottom. And here's a nice case. Pavement structure bottom is here. There's also inner slope angle, but pavement structure bottom is the red one, and ditch bottom is here. And now on the right-hand side, ditch bottom is, you can see, much higher than the pavement structure bottom. And that causes that the water from the ditches, if it's a silty soil, it flows to the coarse grain pavement structure. And the consequence, you can see a wide cracking, because this probably has lost the strength, and during the loading you've been causing shoulder deformation or major shoulder failures. MDI technique has been made also as thanks to ROADEX drainage research. This was made as a sort of spin-off to New Zealand. We used this ROADEX know-how. We were telling about ROADEX drainage technology in low volume road conference in New Zealand with Ron Munro. We were there, and New Zealand wanted to test how this technology could be used also on New Zealand. We did a pilot where we calculated also a saturation level with the GPR, where you have, and the results were excellent. First of all, we could show that always when you had a moisture under the pavement structure, you have a problem, you have a deformation, and you have a roughness problem. So with the ground penetrating radar, the good part is that it's not only the drainage structures, but you can measure also where the water is really under the road. We've been continuing this work also on Finland, and calculating now the moisture content at different depth. And here's a nice example what happens if you are not sealing transverse crack. This is water is going through the transverse cracks and saturating top part of the pavement structure, and then you can see a very high deformation around roughly 10 meters around the pavement structure, only because of this unsealed crack. And on the other hand, then if you go deeper to the structure, here you can see that, okay, the bottom part of the pavement structure has high moisture content, because most likely this private access road is drainage system is not working, and there's a lot of moisture under the pavement over there. Finally, this MDI technique, this is not in the new e-learning. We will probably upgrade it a little bit later, but it can be shown how the moisture is also infiltrating in the pavement structure. Where I was telling about this snow walls, that this snow wall question is that was very much doubted if the moisture in the snow wall, are they really going to the pavement structures? But what we can show on these results, that this is a LiDAR data from this, and this moisture is now can be seen then when it starts to thaw. So it goes and saturates exactly on this area where you are then forming this ice lenses and frost event later rotting. Finally, at the end, it's an example of e-learning of drainage deficiencies in different ROADEX area. I don't bring any show any examples on that, because you can find yourself where they are. But last three slides I just showed that now how important this drainage is. These results are from drainage Pehko project in Finland, where we've been checking this and finding the key reasons behind the pavement backflow. And three issues out of the seven is you can the common factor is drainage problems, private access road junctions, side ditches, and winter drainage problems. And they are very important, and we've been developing now systems that you can have a method of screening potential section with the drainage improvement. And here's a nice example from Uusimaa area close to Helsinki, where we've been selecting drainage class, visual drainage class of 2 and 3. Then ditch is 10 centimeter higher than the pavement structure problem. Annual rut increase is higher than 2 millimeter per year, when it should be much less than 1 millimeter, and pavement age is maximum 6 years. So these blue and red dots are areas where you could save your pavement structure still. It's young, relatively young pavement, but it's already failing, and the main reason, there's enough witness that the main reason is drainage. So focusing your measures on these sections will save the pavement lifetime, and of course save money. And once we've been showing and starting to apply, these examples are from central Finland from 2015-16, where the annual paving costs were more than 800,000 euro on these areas. We checked these expensive sections and big part of them were due to drainage, improve the drainage management. And after 3 years, we've been able to cut down about 36% of this cost. And from this all this cost, we can say that 20% was thanks to better drainage maintenance. So, as I in the first slide said, that this just shows that this good drainage work always brings your money back. So that was like a summary on this drainage e-learning, and drainage e-learning, like what you can find there, and a few ideas about where we are going now. Thanks to digitalization and new technologies, we can much better handle the drainage, and 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 again, it has been, and it is still in the future, even more profitable work in this road asset management. So thank you.